So here we have our question. We have a 10 centimeter long capillary tube that contains both water, H2O, and heavy water, D2O. I will refer to D2O as heavy water from here on out. So on the left from 0 to 5 we have water, and on the right from 5 to 10 centimeters we will have heavy water. Some information about it: we know that the molar diffusive flux is 2.78 for water, and we know that and then we are also given some information here about heavy water or deteriorated water. So we're going to start to get into our questions. First of all, here's a bit of a let me use this. Here's a bit of a illustration of what's going to be going on. Then that's going to be lifted here. Then they're going to mix and diffuse within to each other. So our first question here, we need to find the mass flux. So what do we have? We know the molar diffusive flux, which is J1, and we can find the molar diffusive flux of deuterium because we know that the molar diffusive flux of one substance in a binary system is equal to the negative of the other flux. So the molar diffusive flux for water is 2.78. So therefore, the molar diffusive flux for heavy water is negative 2.78. And here we have some dimensional analysis to kind of show why we multiply by the molecular weight. And so we see that the moles will cancel out to give us mass over meter squared per second, which is units for mass diffusive flux. And so we are going to multiply the diffusive flux for the molar diffusive flux, of each substance by their molecular weights. And we're going to see that we get these here. And we know that the total mass flux is equal to the sum of each individual flux. So we're going to add those together, and we're going to get negative 5.56. And so we're going to move on here to find our next. Here we need to find the order of magnitude. Excuse me, I'm missing an E there, but order of magnitude of the driving force. And so we know the equation for driving force is equal to the sum of the mole fraction of I times the molecular diffusive flux of J minus the opposite over here, and that's all over the concentration times the diffusion coefficient, Maxwell's diffusion coefficient to be specific. So because this system is binary, there are only two substances in this system. We only have to worry about one contact point at 0.5 at 5 centimeters. So we only have to worry about the interaction between 1 and 2. So we can use that to find. We can then use that to find this equation here, and then we want to simplify that out to kind of decrease the amount of variables we have in there. So we know that as I said earlier, the molar diffusive flux of substance 1 is equal to the negative molar diffusive flux of substance 2. So we can plug that in for J2, and then we know that the mole fraction of substance 2 is equal to 1 minus the mole fraction of substance 1. So we can go ahead and plug that in for Y2. and we can simplify that out to get this equation here, and we can plug in what we have. So we know that the molar diffusive flux of substance 1 is equal to 2.78. Excuse me. And then we know that the diffusion coefficient is 10 to the negative 9. So we go ahead and plug those both in. The only thing we need to find is the concentration here. So just in general, the concentration of water is 55,555 moles per meter squared. So we can plug that in there, and then we can find the concentration of heavy water by dividing the density of heavy water by the molecular weight of it. And so we can then find the concentration of heavy water and then average those out to get 55,528. We can plug those all in and get the overall driving force to equal, 50,065 moles per meter squared. And therefore, we can round out that the order of magnitude is equal to 50,000 here. Okay, so for our last question, we need to kind of plot out what's happening throughout the times. So I'm going to start here with this first row. I'm going to take it row by row. So the first one is to plot the densities for heavy water and water on the axis of the density versus distance. So here at the initial time, we know that water and heavy water have not mixed yet. So we're going to have like pure density of water, which is about 1,000, and pure density of heavy water, as it was told to us, was 1,110. And then we're going to just drop down to 0 as we get to the other side. And so next, as we start to mix a little bit, we'll see the slope become more gradual. And then also there will be, for H2O, as you go over to the 10 centimeter side, there will be a non-zero amount of water over there. And then same for heavy water. There will be a non-zero amount over at the 0 side. And so eventually that's going to keep going until it settles out. And deuterium will have a higher density, of course, and water will be slightly lower, but they will settle out. And yeah, so the deuterium will kind of sit lower. Just kind of weird to think about water sitting on water, but the water will sit on top of the heavy water because it has a lower density. So next, we have our concentrations. See if I can zoom in this a little bit more. Have our concentrations. So we see that concentration for, as I found earlier, concentration for water is 55.6. And the concentration for heavy water is 55.5. And so, again, same as last time, they're not yet mixed, so they're going to be at their full concentration before reaching 0 once they get to the other side. And then as time goes on, as they start to mix, they become a non-zero amount once they reach the other side, before eventually settling out over here. And again, the difference in concentration is very small. But yeah. And then next we have our molar diffusive flux here. So we have, until you reach 5 centimeters, you're not going to get any flux because they have not mixed yet. So you'll see the molar diffusive flux happen at 5 centimeters. And there's going to be a very drastic slope into those relative diffusive fluxes. And then as time goes on, the slope into those fluxes will become less steep until they eventually flatten out, because there will be no more flux, there will be no more mixing, it'll be settled. And then next we have our mass flux. We know that the overall mass flux we found earlier is going to be negative. So at 5 centimeters, you will see a steep slope into the negative mass flux, and then over time, again, same as the previous ones, the slope will become less aggressive until it eventually flattens out into equilibrium. All right, and that's it.